Okay guys, so let's start another session, and I'll try to keep this in a span of say 45 minutes, and I'll try to uh, finish this module 2, chapter 1. So module 2 has close to 10 chapters. uh, if I'm able to finish all these chapters in one videos, it will be easier for everybody to go through them, but I will not try to rush as well. So as soon as I say hit 40 minutes to 45 minutes, I will take a pause and then we'll put it into another video. Okay. So the chapter 1 of module 2, so the name of the module 2 is called tools and techniques, and this is kind of a very mathematical statistical module where each topic or subtopic in this module goes into uh, takes a deep dive into one or the many techniques in machine learning, or some of these models that we'll create. At the end of the day, it is going to be some algorithm, so it's going to be getting a little deeper. It's going to be a little mathematical, but let's get started. So the chapter 1 of tools and techniques is it's kind of the overview chapter. So it talks a little bit about everything, and it will give you a basic idea of all of these machine learning techniques on a high level. It's a very important chapter. You should expect a couple of questions from this chapter, and it is very important to have a thorough understanding. Some of you may already know a lot of this, but there is nothing wrong in going through all of this again. So we start with the basics of machine learning, and so let me start at what exactly is machine learning. you know so machine learning is nothing but recognition of, or I'll say, recognize patterns in data. Okay, so this is all what machine learning is all about. And when I say machine learning, it includes the newer forms of AI, etc., etc. So it is recognition of patterns in data, and this data can be very high in volume. Okay, because if it is a small set of data, you can put it in an Excel and you can find the patterns yourself. But when the volume of the data becomes large, you need machine learning to find those patterns. So machine learning will help you to understand or analyze large volume of data. That is the first thing that a machine learning algorithm will help you. It will also help you to navigate non-linearity. So when I say non-linearity, what it actually means is that not all the data can be linearly distributed or correlated. So if there are some complex forms of relationship between variables, etc., machine learning will help you to understand that as well. Then not all the data is clean data, not all the data is something that you can just use it as it comes. So machine learning also help you with the navigation of, or I'll say navigate, bad data. In fact, data quality is one of the primary problems when you actually start working on projects of machine learning and you see what kind of data is given to most of the data scientists. And it also helps you to reduce the complexity of say, I'll say, dimensionality. So what happens, for example, if you are trying to find a pattern or find a behavioral pattern for some process which has, say, hundreds or thousands of parameters. So if you want to bring that down to some reduced number of parameters, say 10, 15 or 20 of them, machine learning can also help you with all of that. And machine learning is used everywhere today. So it's not that it is used only in engineering colleges or science projects. It is used everywhere, right from image recognition. So not just the cats and dogs examples that you see everywhere, but also image recognition in terms of, it can be x-ray images in some kind of, say, medical devices. So medical devices probably is going to be the largest consumer of machine learning, especially the visual data, where assisted analysis can be given to some of these radiologists, where if there is a hairline fracture or things like that, it can be easily detected by a machine. There are a lot of use cases on the lines of NLP. We already use ChatGPT and other things, but text processing is another place where machine learning is used. Machine learning is very heavily used in the banks and financial services, so a lot of credit scoring and a lot of, say, fraud detection. So, and the use cases are infinite. These are some of the examples that I'm giving, that machine learning is used everywhere. Now we have been there is a lot of conversation around machine learning, statistics, and then econometrics. So before we navigate this course further, it is also important for us to understand what exactly is the difference between these methods. And statistics, I will say, is in between machine learning and econometrics. So what happens in econometrics is that, let's suppose you want to model a behavior. Okay. So when you want to model a behavior, you go to some, say, domain experts, and the domain experts, they tell you that it's a function of some parameters, parameter 1, parameter 2, parameter 3, etc., etc. So your data generation process, or if your output variable is y, this data generation process is estimated by domain knowledge, estimated by a group of experts. And these parameters can be, these group of experts can, based on their expertise, they can use these parameters, or they can find these parameters. For example, if you want to find out the credit worthiness of an individual, some domain expert will say that, I want to use the credit score, I want to use some other metric, which gives us some kind of a indication of the credit worthiness of that individual, maybe the balance that he has, or liquid cash that he has, or how many properties the person is having. So in econometric models, the function is derived first, and once we have a kind of a draft function, we create something called as a null hypothesis, which is represented by H0, and an alternate hypothesis, which is represented by H1. So H0 says that this is correct, and H1 says that this is not so correct. And then there are some statistical methods, and I don't want to get into those details right now, but then there are p-values and those kinds of ANOVA analysis, which will statistically prove whether H0 is correct, or H0 is not so correct. So that happens in econometrics. In case of machine learning, what happens is that instead of estimating the data generation process, you use data itself to estimate the data generation process. So you don't need that kind of a domain expertise, or you don't need any person to tell you what parameters are important, what parameters are not so important. And this data itself is distributed into, say, D1 and D2, so that the validation. For example, in case of econometrics, we were using this H0 and H1 as hypothesis and trying to test this. The validation of the data generation process P is also done on a hold set, which is a portion of the data itself. And statistics is something that is a mix of two, or happens in between, or when econometric methods were slowly and steadily moving towards computer generated software enabled machine learning methods, all these stats also came into between. So statistics is in between, but the basic difference between econometrics and machine learning is that the data generation process here is estimated by experts, and here the data generation process is generated or is estimated by algorithmic process itself. Okay. And there is some of the terminologies that you may be using as in econometrics as a statistician, and and the um, the terminologies that you use as a machine learning engineer, like he will call that this is an instance, and this person is going to call probably a data point. This person is going to call, say, target variable, and ground truth, and an econometrics guy is going to call dependent variable, independent variable, etc., etc. This is going to be, say, he's going to talk about training and testing, validation, model, and this person may talk about estimation and estimator instead of model. This person may be saying that types of machine learning. So machine learning is distinctively divided into 4 categories primarily. One is called unsupervised, second one is supervised, third one is semi-supervised, and then there is one more which is called as reinforcement. Let's go through them one by one. So what happens in case of unsupervised learning is that there are a bunch of data points, and these data points are unlabeled. So when I say unlabeled, there is we don't have any additional information about these data points, whether they belong to a specific category or they do not. Let's suppose, and each of these data points can be a culmination of a variety of features. Okay, so when I say a culmination of features, assume these data points are for a customer. They are customers data. So your data point is a customer data, and for each customer your features can be like your age of the customer, the portfolio that the customer is holding, the demography of the customer, anything else, whether it is credit score or whatever you want to say, education qualification, etc., etc. So all of these data points, or a culmination of features for these data points, are available, but you don't have an additional humanly intelligently annotated data whether these particular, let's suppose, customers are your credit worthy, and some of the other are not so credit worthy. So that information is not available in case of unsupervised learning. So in unsupervised learning, we use all these data points and we try to find out some of the common patterns in data. And based on these common patterns, we try to put them into separate buckets and say that okay, the I dot dot dot, they belong to one bucket, the X dot dot dot, they belong to second bucket, the Y dot dot dot, they belong to third bucket. Okay, how many buckets, how many categories or buckets, that depends upon the context of the problem that we are solving, and we can decide this on runtime. Where is it used? In the financial world, unsupervised learning is used mostly. I have seen that it is used for segmentation of customers. So when I say segmentation of customers, if you have a bunch of customer, you want to profile them, who is risk averse, who likes to take risk, who is and based on all those segmentations, you can give them you can consult them, or you can tell them that this is the right investment for their kind of a behavioral profile. So segmentation is one thing. The other application of unsupervised learning can be in anomaly detection, which is also kind of segmentation itself. But in anomaly detection, let's suppose you, for a particular customer, you say that his behavior is defined, like the circle is the behavior of the customer for customer X, and if there is a transaction T that happens within this behavior, that's fine. If there is a transaction T that happens outside of this behavior, you can flag this as an anomaly. So we can use unsupervised learning for anomaly detection as well. Coming to supervised learning, which is the most powerful form of machine learning and the most widely used form of machine learning. Here in this case, again, you have all these DIs, which is data points, and let's not put additional features, because now we know that each of these data points comprises of a bunch of features. So with all these data points, there is also a label. Okay, so we also have labels for each of these data points, and these labels can be depending on the context. These labels can be different. So if it's a visual data, you can say that okay, this is a cat, this is a dog. And if it is not a visual data, let's suppose this is a text data, you can, if it is a let's suppose part of speech kind of a problem, you can say this is a noun, this is a verb, this is so and so. In case of the problem that we are discussing earlier, we can say yes, this person should be granted the loan, this person also should be granted the loan, this person should not be granted the loan. And who decides labels? They are SMEs, they are domain experts, they are the people who have been probably doing this process from a long time without using machine learning, and because of their years of experience, etc., they have found out a method outside of machine learning method which can tell them that what it needs to be labeled as what. So that's the labeling side of things. Then if we are interested in finding the final output, which is nothing but the labels, as a continuous numerical output, then this form of machine learning is called as regression. Okay, so what I meant to say is that if there is a data point I, which is nothing but a set of features, and we pass them to a function lambda, the output is going to be a numerical value. So assume that you want to estimate the price of a property, and your features could be square feet, the location, which includes city, country, state, etc., maybe the age of the property, if there is a legal litigation or not, etc., etc., and you find out the dollar value. So this is when your final label needs to be a continuous numerical value. This is called as regression. And then there can be different forms of regression, that if it is a kind of a time averse regression, then it is called time series. So let's suppose if you want to do some analysis or find the market value or index value, or the value of a particular stock day in and day out, where your time is also one of the key features, or your lambda of time t is dependent, or is proportional to lambda of time t minus 1, then it is kind of a time series data. But net if the label is a continuous numerical value, it's called regression. If your label is a categorical value, it can be numeric or non-numeric. When it is categorical, it can take one of the many distinct a finite set of possibilities. Then it is called as classification. So as I said, it can be a cat or a dog, it can be loan worthy, not so loan worthy. So when the final output of the label is a categorical value, it's called as classification. It's a discrete kind of output. So where can classification help you? In credit risk, when you are trying to find out the credit worthiness of an individual. And the regression can also be one of the, let's suppose you want to find out the, if somebody wants to buy a house and you want to give a credit to fund that house, so the estimated value of that house can still use regression, but the final credit worthiness of that customer and the value that he is seeking will come from classification itself. So that is supervised, the most popular. We'll talk about supervised mostly entirely in the course. The next one is the third category is semi-supervised. So semi-supervised is nothing but a culmination of supervised and unsupervised. So generally in real world, most of your data comes like your unsupervised data. But without domain experts and without supervised, it becomes very difficult for us to process that data or make sense out of that data. So a lot of times, there is some proportion of your data that is supervised, that is labeled. Let's suppose it is a kind of a classification problem you're trying to solve. So there is certain percentage of data that is supervised, and the remaining percentage of data is unsupervised. Now, how do we handle this kind of a data? There can be multiple methods. One method is that you forget about unsupervised data. You use this data and you start building models on this data. This is possible when X is very large. Okay, let's suppose it has millions of data points, and this also has millions or probably tens of millions. But even if you forget this portion of data, you still have a substantial amount of data. So that is first type. The second type can be that you take this 100 minus x of data and you process this as an unsupervised learning, clustering, segmentation, whatever I was talking earlier. So that is, and you ignore this side of data. And the third category, which is the most practical used, and logically also it sounds that we should do this, is that when you use a combination of both. So sometimes what you must use is that you make an interim model from your labeled data, and then you use that to label your unsupervised data. So you put some kind of a pseudo labels, and once you have these pseudo labels, almost your entire data, 100% data becomes labeled, and then you can use this as supervised learning. There are algorithms like active learning, etc., which can make use of this kind of a combination. And this process is also can be of multiple forms. We will go through those multiple forms in some of the subsequent chapters. So that's the semi-supervised. The last category of machine learning, which is the fourth category, is called as reinforcement learning. Now this is slightly different from the first three categories, where we were talking in terms of data points, whether those data and each data point is a combination of features, and whether those data points are labeled or unlabeled. In case of reinforcement learning, you visualize this as some kind of a game that you are playing, okay, or some kind of a real life decision making that you do. Like, let's suppose you are driving through the traffic on, so what happens in whether you are driving your car from your home to office, or you are playing a game, what happens is that you are, let's suppose you are in a state S1, you take some particular action. The action in case of game can be, let's suppose you are playing a chess game, and you say that, okay, let me start my game with Sicilian defense, or whatever is your favorite opening, and then you go to say state 2, and then you take another action, a dash, and you go to S3, and you keep doing this till you reach an conclusive end state, and you can either win, you can either lose, or it can be a draw. In case of traffic, on each red light or each signal that you have to make a choice whether you want to take a left or take a right, or go straight, or take a U-turn. You take some action at that point of time, and finally you reach office. You can reach office on time, before time, or after time. So this is, you visualize this as a set of states and a set of actions that you take. The only thing that we will be, the kind of a labeled output that we get is in the end, if like it's a win or a lose. And if you win, let's suppose, so in case of reinforcement learning, what happens that in case you win, then all the actions that you have taken, they are incremented by a particular score. Okay, the probability of taking those actions in that particular state increases positively. In case you lose, then your probability of taking that action in that particular state decreases. Okay, and all of this is happening in a particular environment E. So environment E can be like you are navigating through the traffic in a particular city, like say Pune, when in summers, morning 7 a.m. Or because if you are navigating through the traffic in Pune 7 a.m. in let's suppose a particular location in Pune, when there is no rain, versus the environment when you are navigating it in say Bangalore and 6 p.m. and let's suppose it is raining, it's not the same. So the environment in which you operate is also important. The environment, it can be static environment or a dynamic environment. So all those integrities, let's not get into all of that, but it's a set of states, okay, and in each state there are possible actions, and then you start with say some random initialization of these actions. Let's suppose there are 3 actions that you can take at a particular state, that is, take a left, take a right, go straight. You said, okay, let's suppose this is 0.33, 0 is 0.33, 0 is 0.33, and then once you reach your end state and you do this process iteratively a couple of times, you end up changing these probabilities, and let's suppose this becomes 0.9, and in state 2 this becomes 0.9, here it becomes 0.9. You know that, okay, at this junction it is better to take a left, at this junction it is better to take a right, at this junction it is better to go ahead. So when you find the possible best actions in a particular state, operating in an environment E, that's something called as reinforcement learning. So ideally, these are the four forms of machine learning that you should be aware of. There is not a fifth one, but there is another way to look at some of these algorithm is parametric and non-parametric. So parametric is something that where you need labels, and you need some kind of a domain information, and that my final output is going to be a function of a particular features. Okay. And in non-parametric, you just put all the data across some kind of a complex function. Let's suppose it's a deep learning function, and you find out the label. So you don't worry about what parameters are important, etc., etc. This needs domain information, this doesn't need domain information. Okay. But this is less categorized. But since GARP talks about this in the reading, GARP talks about this in a small paragraph, it's good to know that okay, parametric and non-parametric could also be one of the forms of machine learning classification. Okay, so we are done with the classification of machine learning. Next topic, as per the syllabus in this reading, is on EDA, which is a very important topic in practical sense also, when you actually work on machine learning problems and with respect to exam also. So EDA stands for exploratory data analysis. Okay, so at the end of the day, whatever you predict is going to be dependent on what data you have. So it is very important for you to do an data analysis exercise. So exploratory data analysis consists of 4 parts, and generally these 4 parts are done sequentially. So the first part is with respect to collection of data. Very, very important. You need to know where you are sourcing your data from, how you can source your data, etc., etc. We'll get into the details. Then is the cleaning of data. So your data is not that good, it has errors, it has loopholes, you need to clean it. It can come from various sources, you may want to reconcile it. The third is visualization of data. So human mind is more capable to understand data when we are able to see it in forms of graphs and charts and other 2-dimensional or at the max 3-dimensional visual forms. So visualization helps. Visualization also helps with cleaning of data. Okay, so this can go in some kind of an iterative fashion. And the fourth part is the analysis of data, which is feature engineering, etc., etc. Let's go into them one by one. So in your data collection, first and foremost thing, as I was saying, that your raw material in this entire analysis is data. So if there is a garbage in your data, garbage in implies garbage out. So if your data itself is not good, your analytics are going to be even worse. So it is very, very important to make sure that your data is collected in high volume, clean, something that is and relevant, relevant to the problem that you are solving. Data, before we delve into the collection activities, just understand that data we are talking can be structured, data can be unstructured, or data also can be semi-structured. And the way to process this data, whether it is structured data, unstructured data, or semi-structured data, is also different. So when I say structured data is mostly, say, numerical data or categorical data, okay, or some kind of factual data. So structured data is easy to process. Numerical data can be okay. You are talking about the customers So let's suppose we are talking about customers metadata, and let's forget whether there are some GDPR rules and all of those things, but you have customer name, you have customer age, you have customer city, you have so all of this data, this is structured data. Okay, because you know the age of the customer is 45, he lives in Pune, he or she lives in Pune, then the gender of that person is, let's suppose, male. So this is structured data, easy to process, and name is there is some name. In unstructured data, it is mostly, you know, text data or some kind of image or any other multimedia. So you may not be able to get a lot of sense out of it directly if you process this as numerical stuff or categorical stuff. So in case of customer information, let's suppose you want to you know, let's say I'm saying customer plus plus or customer additional customer data. So there can be a picture of the customer, there can be his voice calls, he has called the call center and said that, you know, he's happy or not so happy. There can be some emails that the person would have written, you know, and especially these two things can be one of the 7,000 languages. So somebody can write in Hebrew, somebody can write in Hindi, somebody can write in English. So there is a lot of language processing part as well, you know, and voice calls, people can speak in different languages, and then within each language people can have a particular accent. Okay, I can talk with a Indian English accent, somebody can talk with a British English accent, somebody can talk with a Chinese English accent. So this data is more difficult to process and clean and understand. So that is unstructured. Semi-structured data, again, it is a combination of structured and unstructured. So let's suppose there is a comment section in the form or wherever, you know, let's suppose when you're trying to enroll a new customer and you have put some you know, you have asked the person to comment. Person can say that, you know, I am very happy with the enrollment process and I have opened a savings account in the bank, and you know, initially I'm depositing say $10,000. Okay, now there are portions which are more structured, that the deposit amount and the what product the customer is choosing, but then there are portions of data that is not that structured. So how do you process this is also kind of different, and this is just one example. There can be more complex examples where, let's suppose there is a table in a document you are trying to process. There is a table and there is some text around it. So this tabular data is structured data, and this textual data is unstructured data. And if you want to culminate all of this together as a document data, that is semi-structured. Okay, so that's how data can be structured and semi-structured. Okay, before we get into anything else, let's also talk about longitudinal data and cross-sectional data. This is also one way to categorize data. So longitudinal data is a set of data which is where the sequence of data is important. So if Nifty today is operating at 24,000 points and yesterday it was operating at 23,900 points. So Nifty is a stock market index in India. So today it is operating at this, at T minus when it was operating at this. So my index today is a function of index yesterday. You know, that cannot go drastically. The sequence of data is important. Okay, if I have some data points, let's suppose I have a data point which says that, okay, what is the index value? And then there is like 24,000, 23.9, 22,000, dot, dot, dot. I cannot just take this here and move this here, and the sense of the data will change if I change the sequence of information. So that's longitudinal data where your sequence is important. In cross-sectional data, sequence is not dependent. So sequence is not important. You can consider, even if you shuffle the data, it will not make so much of difference. So let's suppose there is a pool of customer data, and same one which we are talking, DIs. If we change the sequence of index I, it will still make the same sense. So that is cross-sectional data, and this is longitudinal data. So there is one very important reading that I'm going to tell now, which is something that has been consistently being tested in the exams as well, is about this categorical data. Okay, so we spoke about, so we are talking about exploratory data analysis. Within exploratory data analysis, we are talking about the collection part of exploratory data analysis. We spoke about structured, unstructured, semi-structured data, and cross-sectional and longitudinal data. And data can be numerical, it can be categorical, or it can be textual, or other formats. And in categorical data, now when it comes to categorical data is very interesting data, and they have categorized or they have broken down categorical data into various forms. So when I say categorical data means that your data needs to fit into a set of categories. Okay, so if you buy a t-shirt, it can be small, medium, large, and nowadays there can be extra large, extra large, extra small, etc., etc. It can be gender, which is male and female. It can be anything. As you're doing sentiment analysis, it can be positive, neutral, or negative sentiment, etc., etc. So this is how categorical data is. So let's start with say category 1 of categorical data, which is nominal scale. So in nominal scale, the order is not important. The order of categories is not important. Okay, so let's suppose we are talking about so it's a data set is about cars, and in this data set there is one feature which talks about the color of the car. The color of the car can take values like, say, white, red, black, yellow, dot, dot, dot. So the order in which these categories would appear is not that important. And let's suppose tomorrow we say that, so because at the end of the day, most of the algorithms would process numbers, not your white and red and black. So one way to encode these labels is that you say white is 1 and red is 2 and black is 3. But to make sure that the algorithm does not misinterpret this, it is always better that you keep separate columns. Let's suppose there are 5 colors that your vehicle is offering. So you put white, you put red, you put black, you put yellow. Let's suppose these are the 4 colors. And if it is a white color, you make this as 1 and make them as 0. If it is a red color, you make this as 1 and make this as 0. So all of these columns can take either a value of 0 or 1. And if it's a dual color, you can probably have white and black, which is white and black, and then this and this, etc. Whatever is the domain of the problem. But if you look closely, the order of these values doesn't make sense. Red can come before, white is later, all of this. So this is nominal data. The second category is ordinal data. So in case of ordinal data, order is important, of course. Otherwise, why would it be a separate category? Order is important, but interval might not be same. So let's suppose there is category 1, category 2, and category 3 and category 4. Now order is important, so this needs to be in the same sequence, but the difference between say category 1 and category 2 and the difference between category 2 and category 3, they may not be same. Okay, for example, if there is a text and we are saying that okay, this is negative sentiment, this is neutral sentiment, and this is a positive sentiment, so it is not always the same that the polarity, the difference of polarity here and the difference of polarity here may be same, may not be same. So this is the second category, which is ordinal data. Order is important, but the difference of values is not the same. The third category, and we are going step by step. So in the first category, order itself was not important. In the second category, order was important with the but the interval were not important. The third category is interval data, where your order is also important, your interval is also same, but there is no 0 point. Okay, so that means that the 0 value does not signify much. Let's take an example. Let's take an example which has a 0 value. So we are talking about temperature. Okay, so temperature in Celsius, temperature in Fahrenheit, mostly in Celsius and Fahrenheit. Now if I say that the temperature of Pune is 24 degrees today, and then I say that temperature of Bangalore is, let's suppose, 22 degrees Celsius today. So and if I say the temperature of Delhi is 26 degrees today, then of course the difference between these two temperatures and these two temperatures is same. But if today I'm saying that somewhere in the Himalayan region in India or somewhere in Europe the temperature is 0 degrees, but maybe in Antarctica the temperature is minus 30 degrees. So 0 is just a number like anything else because it falls into that scale, but 0 does not signify anything much. Okay, and the same is true for latitude, longitude also. If there is something which comes at 0 degree latitude or 0 GMT, in case of time, GMT, it is just a location on the earth. It doesn't signify much. So that's the interval data. And the last category, last but not the least, is the ratio data, where order is important, intervals are important, and there is a significance of 0 value. Let me give an example so that you understand this more better, and you should expect some questions here. Let's suppose we are talking about height of buildings. Okay, so if we are talking about height of buildings, then I'm saying this is 100 meters, this is 120 meters, this is 140 meters. The interval has to have a significant, the interval needs to be consistent. If I say the height of the building is 0, that means it does not exist. So 0 has a value. If we are talking about people and we are saying the height of the person is 0, that means the person does not exist. Yeah, even molecular and submolecular things will also have some height and weight and all of those things. It might be very, very minimal, but it will not be equal to 0. So 0 has a value. So so these are the 4 categories of measurement or the scale of data measurement in categorical variable. And I was mentioning that the data that you get is, the quality of the data is generally bad. So you would need to do a lot of stuff to clean that data. So when I say clean the data can have duplicates, So finding duplicates is not that difficult. It is a kind of a simple exercise if it is numerical or categorical values, even if there are multiple of them. But if it is textual values, finding exact duplicates might still be easy. But if you want to find say some values that are paraphrases of each other, it may still need some kind of a processing, that somebody saying the weather is nice and somebody saying the climate is wow. Both mean the same thing, but how do you get away with one of them? Okay, so that's about the duplicates, because unless and until there is not enough variety in your data, and if it is just the replica of each other, the models and models will not be so good. So that's on the duplications or deletion of duplication. The second major issue in data cleaning is on the missing values. So what happens a lot of times, because of multiple reasons, some features may have a missing value. Okay, let's suppose you have census data, and whether it is a data entry problem or it is some other problem, you may see that the age is missing for some of the people. uh, and if it is there can be sometimes a no value or a missing value can have a practical significance, where people have intentionally missed it. For example, if if it is an let's suppose in the census data, if we are collecting some kind of a health record of an individual, and if it is missing, it may mean that the person is no more or the person is deceased. But a lot of times there can be missing values that are not intentionally missing, but we may have to find a substitute for those values. And based on scenario to scenario, so it is not like one size fits all. Based on scenario to scenario, we can replace the missing values by their mean, mode, medians, or do some kind of a classifier on the values where there are enough information, and then predict the missing values. Or we can sometimes, if the missing values are insignificant or very small proportion, we can also get away with them, we can also delete them. The third problem, or the third thing that we need to take care in case of data cleaning, is with respect to outliers. So sometimes, mostly because of a typing error or those kinds of things, you can get some nasty values in your data set. Let's suppose there is a age and you find something called as 507. Now a human mind will come to know that this kind of a age for an human being is not possible. But when you let it for the algorithm to analyze, this kind of a value in your age is going to heavily impact your mean value of that system. It's going to be, so the mean value of your age is 60. Putting this kind of a value, depending upon the size of the data set as well, but if the size is not large, or if these kinds of values are, the errors are much more, your analysis is going to go for a toss. So finding anomalies or outliers and deleting them or getting rid of them is very important before you actually get into the analysis of data. Let's talk about data visualization for a while now, and you will understand that as we visualize data, some of these problems like your outliers or missing values can also be processed or interpreted or solved using visualization. So what generally, a human eye or a human mind can visualize the data in 2 dimensions or maximum 3 dimensions. So when you put graphs or some kinds of other things, whether it is charts and or any other visualization tool. Nowadays there are a lot of sophisticated visualization tools as well. So when you plot your data into all of these graphs and charts, you will be able to find out the real world interpretation of that data. So most of the times what we do is we do the histogram analysis of our data. So in histogram, what histogram does is that it will try to create the frequency of the variable, and it is trying to plot the in the on your x and y direction. It will have your, you know, the variable that you want to visualize and the frequency of that variable. So let's suppose x can take value from say -15 to +45. Let's say this is the weather data, and most of the times, since I'm in Pune, let me take the example from Pune. The value is, let's suppose, 30 degrees Celsius. So this is going to be much bigger, because out of 365 days in a year, let's suppose 150 days I am close to 30 degrees, and then there are values more than 30 which are much less, and 45 much lesser. And similarly, when I go on to the negative side, let's suppose when I say negative side, maybe 25, 27, 24, 23, and maybe maximum is your, or minimum is your 10. So this gives me some kind of a visual interpretation that the weather in Pune follows this kind of a trend, and the most frequently occurring value is 30 degrees Celsius. So this is an histogram, and once we plot histograms, looking at the graph of this histogram can also give me some kind of a probability distributions, that, you know, that this is how, this is a distribution which is called as a normal distribution. We all know what is a normal distribution, and for some other behavior, if I can find it as left skewed or some kind of a, say, Poisson distribution, this distribution itself can give you a lot of insights on how this particular variable can behave. So that's why data visualization is very important. There is also something called as a box plot, where you find your say median value first, which is called as second quartile, and then you find out you know, the top 25% or the bottom 25%, which is the quartile 3 and quartile 1. And once you have these values, and then the difference between quartile 1 and quartile 3 is called as interquartile range, and let's suppose that is I. You multiply I by 1.5, let's suppose, let's call it as y, and then you find ranges either side of q3 and q1, which is y distance, and any data that comes outside of these two positions is termed as outliers. So we were talking about how bad outliers can be. This kind of a box plot or a visual technique is used to find out outliers. So if you do this kind of an exercise, your outliers can be easily detected and deleted from your input data. We also can also you know, do some kind of correlation analysis between the data points or between the attributes. So let's suppose there is an attribute 1, attribute 2, attribute 3, attribute 4, and we plot them with each other, and we try to find out how these attributes are correlated with each other. So of course attribute 1 and attribute 1 are going to be correlated with each other, and same is true for 2 and 3 and 4. But what we are really interested is that how is attribute 1 and attribute 2 related to each other. So it can have different values, it can have, you know, let's suppose this is how it is. And attributes which are highly correlated with each other, so A1 and A3 in this case, needs a different kind of a processing, and that's where this kind of plot, this kind of visualization. So here it is a numerical visualization, but I can also plot this in some kind of you know, correlation graphs, and once I see straight lines, diagonal lines, I'll see that okay, these are correlated values, and then I need to understand that A1 and A3 are very highly correlated, so I need to process them slightly different. So that's the intent of doing a visual analysis of your data, because it helps you to process data, to interpret data, because human mind can understand visual things better, and it will help you a lot. The fourth part where we are talking about is data analysis. So assuming all of this is done, then, and all of this is a part of EDA itself, exploratory data analysis. In case of data analysis, there is something called as, the first thing that we generally do is feature engineering. So features, attributes, independent variables, these are all same thing but spoken in different context. So feature engineering means that all your attributes or all your independent variables that we are trying to model need to be processed or need to be engineered. So first thing is that we need to understand whether we really need to take all of the attributes that are given in your data. So let's suppose if your data set uh, has say attributes, 100 attributes, or the column names, or let's call them features from now on, just to avoid confusion. So if they have 100 features, you may not need all 100 of them. It is computationally expensive, it is not that relevant. As we said that if A1 and A3 are highly correlated with each other, we can only take one of them. So feature engineering talks about elimination of features, reduction of features, and also putting them in scale. So let's suppose some of your features are categorical in nature, and I'm just saying categorical, which can again be nominal and interval and ratio, whatever we discussed. But if they are categorical in nature, and I need to put them through a model. So let's suppose there is a male and female, which is my categorical feature. How do I put this in my in my uh, in my data? Should I say male as 0, female as 1, or the vice versa? So it can have repercussions, because 0, whatever we multiply this with is going to give you 0 only. So most of the times, or what we do is that we put the value, we'll create new features, that whether it is a male, whether it is a female. If it is a male, we put it as 1. If it is not a male, we put it as 0. And so, so that's how. So in this particular case, since it is a binary feature, this is mutually exclusive. So both of them cannot have 1 values. But in some of the other scenarios, let's suppose risk factors, or let's suppose the risk of an individual. If we are putting them into 4 categories, 0, 1, 2, 3, and 4, 4 being people who can take high risk, and 0 people who cannot take risk at all. So putting them in these kinds of numerical fashion can create problems in your further analysis. So we generally say that, okay, is it a category 1, is it a category 2, it is a 3 and 4, and all of them can only take values 0 or 1. So if it is 1, all of this will be 0, and that implies that this person is of first category. So that's how feature engineering happens. That's how feature engineering happens in most of the scenarios. Then there can be scenarios there where you may have to convert some of your numerical data into categorical data when you are not so much interested in knowing the nuances of numerical data. Let's suppose age is a numerical data, and you are doing some kind of a risk analysis. So all you want to know whether it is the person is less than 18, a person is between say 18.01 till 40 years, which is when you can make the most amount of money. Then you are 40 to 60 years when you are still making money, but you are also planning for your retirement. And then you are 60 plus, you are probably retired. So you are only interested what category this lies in, the person lies into. And So you convert your numerical data into categorical data. So that's how you process your categorical data. In case of numerical data also, there can be a lot of processing that you may have to do. For example, if you have, I'll tell you why you need to process your numerical data first. Let's suppose you have in market index values, and in India, if you're talking about Nifty, this can be like 24,000. So market is at 24,000 these days. And let's suppose you also have age, which can take values from say 18 to 55 in most of the scenarios. So if you keep this data as is, the quantum of numbers here is way larger than here. So it is difficult to interpret. It is it is not going to give you some kind of a numerical stability if you want to keep them as is. So there are two methods that we generally employ. One is called as standardization of data, and one is called as normalization of data. So standardization is very simple. Your new value of x is going to be subtract the mean and you divide by standard deviation, which means that your new values will have your mean as 0 and your standard deviation as 1. So that's how your data can get standardized. In case of normalization of data, what you do is you find the difference between x max and x min, and then you subtract your data with x min. Okay, so that's how your chart comes. So that's how normalization of data happens and standardization of data happens. This what to use in what scenarios depends upon what you are handling. If it has a lot of outliers, it is better to standardize your data rather than normalize your data. But in some other scenario, you may want to normalize your data rather than standardize your data. So it all depends upon where you are and what you want to achieve. But it is always good to either standardize or normalize your data so that it it comes to the normal scale. Why you want to do all of this? As I already said, it will help you to give some kind of numerical stability to your model, because all your numbers will come in the close range. It is also very easy to interpret, because otherwise if you in the later stage, if you build a model and you find some of the weights or your distribution of parameters or distribution of weights, that okay, 60% is here, 40% is here, and if your features itself are not normalized or standardized, you will not be able to interpret those weights easily. So it is easy to interpret if your numerical values are either normalized or standardized. And if you have say some of your data kept as out of sample, it can also help you to understand how your normalization behaves with respect to out of sample data. So these are some of your advantages for using this numerical standardization and normalization. Let me do one more subtopic, and then we'll take a break for the day, which is around data transformations. So, and this is all a part of EDA, so I don't want to break this into two separate sessions, and we'll close in next 5 minutes or so. So sometimes your data or your raw data may be very skewed, or it may, if you try to plot it or visualize it, you may see some random things. Okay, now if you want to really put this into perspective, you may want to do some kind of a transformation on this data. So there can be multiple types of transformation, but let's suppose you want to do log of data. So a log transformation may help you to put this kind of a data into some normalized data, or data that follows some kind of a distribution which is easy to interpret. So that's where your transformations help. It can be log, it can be FFT transformation, or based on your data. And as you analyze more and more data, you will be able to find out what kind of a transformation is most suitable for what kind of a circumstance. So uh, one thing that you need to remember, important for your exam as well, is that while your numerical standardization or normalization is not going to change the change the pattern of data, but your log transformation will change the pattern of data. Okay, so the way your underlying data is, normalization will keep it as is, it's just going to change the scale. But when you transform your data, your pattern of the data and underlying pattern of the data, or the distribution pattern of the data itself, will change. I think I'll take a break now. There is a little bit that is left in module 1, which is not so much. We only need to cover PCA, principal component analysis, but since this is a big topic, I don't want to cover this today. It will unnecessarily make this session very long. Then we'll also talk about this train and test and validate data set, where you break your data into these three portions. What is the importance of each one of them, and then some kind of what kind of a software techniques we should use to do all of what we discussed. So that's remaining probably 20 minutes session. I'll put one more session as 20-minute session, but this is going to be a long session. But I thought that since all of this exploratory data analysis are related to each other, I thought I'll put this in a single video. Thank you.